All right. I think we should get started. I know this is not the perfect timing for for audience from parties for participants from Chinese time zone, but I think we should get started. But I can also see that participants are triple in. All right. I think the our speakers are complete, and yeah, I'm gonna share my screen and give a really brief introduction about our session. First of all, welcome to the third International Industrial Ecology Day, and also welcome to our session, where we dive into the world of energy and environmental system modeling. This is because the motivation for having this session is because we are grappling with urgent need to combat climate change and achieve sustainable development goals. And so our focus today is on the innovative models that guide our ways toward a greener and more sustainable future. And so in today we have 5 speakers, and our speakers here are here to share insights into how energy and environmental system models can help us make a difference. And from industrial decarbonization to energy transition and air quality. In our session, we will explore diverse topics that shape our journey towards, carbon neutrality and sustainability. And more importantly, our 5 speakers will walk us through the power of scenario analysis, because their models, or the energy and environmental system models, are not just numbers on the screen. These models can help us, or help policymakers and stakeholders to map our pathways toward carbon neutrality and help us identify important trade-offs, along the way. So again, thank you so much for joining us on this exploration, and let's get started. Um, and before we start, I would like to give a very, very brief introduction about our 5 speakers. So today we have Professor Chuan Zhang from Peking University, and we have Hetong Wang and Professor Joshua Li from Shandong University, and we have Li Rongliu from University of Surrey, and we have Hanchen Dai from Peking University, and our last speaker is Xiaohui Zhang from Beihang University, or YASA. And after our 5 speakers presentations, we'll have a plenary discussion to reflect on what we have learned over the 5 presentations, and also what we are taking away from the 5 presentations, and importantly, what we should do differently moving forward. And without further ado, I would like to hand over the floor to Professor Chuan Zhang. Yes, Professor
Okay.
Zhang, now you
Yeah.
can you share your screen?
Yes. I think you needed to stop sharing. Okay. Yeah.
Yes, I will stop sharing. So while so Professor Zhang is putting up his slides, I would like to give a very brief introduction about Professor Zhang. Professor Zhang is currently assistant professor working at Institute of Energy at Peking University. He also has a joint position at Institute of Carbon Neutrality. I think today he's going to share with us his recent work on net zero America, also how this integrated assessment model can be applied to other contexts. And floor is yours, Professor Zhang.
Okay. Thank you for the introduction, Professor Cao. And actually, it's my great honor today to share some of my research and thoughts on this International Industrial Ecology Day. And today, my topic is integrated multi-dimensional and multi-level energy system analysis and its application. As Professor Cao mentioned, my name is Chuan Zhang. I'm currently assistant professor at Peking University. So a very brief introduction about myself. I did my postdoc at Princeton before joining Peking University, where I did the Net Zero American Study, which is a large project involving around 30 people to, kind of draw a technical roadmap for how to transfer US national energy and industry infrastructure to low carbon future. And before that, I get my PhD training from a Cambridge Cares program, which is a joint program between Nanyang Technological University at Singapore and Cambridge at the UK. So currently, my work mainly focus on co-utilization of fossil fuel and renewable, and also some digitalization of energy system. So I also list my website, and if you are interested, you are welcome to follow some of our work. So the outline of my talk today. So I'll introduce from 5 aspects. Firstly, I'll talk about why energy system decarbonization or why energy decarbonization needs system analysis. And because system perspective is a very important perspective for people in industrial ecology, but for energy researchers, I would like to say it's not as familiar as in that community. So I think trying to let people know the importance of system analysis is important itself. And then I'll try to see what questions energy system analysis answer and how energy system analysis could be good and could be bad. And I'll use a very simple illustrative case study to show the usefulness of energy system analysis and also my own source on energy system analysis. So firstly, I would like to show this very kind of outdated schematic. This is a schematic of energy system from the 1998 a kind of classical textbook from Cambridge University Press. And here it shows, we call it superstructural energy system. You have the supply side, have different kind of energy resources, fossil fuel, renewable, and or other. And you have the demand side, you have the industrial, residential, and the transport. And then in between, you have a very complex, we call it superstructure, which means you can have, let's say, coal to electricity, and then electricity to maybe industry, or you can have coal to, gas or hydrogen, and hydrogen can to industry. Basically, different pathways of using different kind of energy resources for different kind of energy demand. And here, we can see several conclusions. Firstly, is when we talk energy system, it had a high, it had a high temporal and spatial scale. Basically, you can talk about national energy system, or you can talk about, residential or community level, and also each pipeline or each supply chain itself is beyond the technology. I would like to see, when we talk about the utilization, the mining of coal, it is not only about technology itself. It also had related, GDP or employment or this kind of stuff. Help to explain the story why this energy is used in reality world. And when we talk about energy transition, we couldn't avoid talking, we have a triangle which needs to be reliable, affordable, and clean. And in many times, achieving that triangle target is not easy because for some energy is reliable and affordable, but it's not clean. But for others, it's clean and maybe not that reliable. So this is kind of a picture or superstructure of what people think the energy system in 2022 could be when they were at the day 1990. So the black lines are what have been achieved over then, and the red ones are what they think could happen in the future. And interestingly, if you look at the recent research on the future and net zero energy system, this is a paper published on Science by Steele et al. in 2018 in 2018. And interestingly, if you compare the superstructure here in this figure and the superstructure here in that figure, you will find the most technology are actually the same. So basically, it means when when we at today's time scale and we think in 30 years, what do we need for net zero energy system? It is the same to when people are in 1990 and what they think what will be needed in 2020. So this is an interesting phenomenon I found. So basically, it means in terms of energy technology innovation. So what we think could be used in the future are already they're already there for for 30 years, but the thing is it hasn't been materialized or hasn't been largely deployed in a real system. This is a challenge for energy transition, I think. And when we talk about the pillars for energy decarbonization or energy system transition, we all know we have six different, I summarize as six different aspects, but maybe it can be combined in different ways. Firstly, you need to increase energy system efficiency or productivity through maybe electrification on the demand side, and on the supply side, first you need to use a lot of clean electricity like solar and wind, and also you need for some difficult to electrify sectors, we still need kind of liquid fuels. So we may need net zero carbon fuels to satisfy that demand. For example, the aviation decarbonization are most likely rely on net zero fuels in the future. And for some, remaining emission from energy system, we rely on carbon capture and storage, and also may seek help from the enhanced land sink. And these are the six pillars we have, everybody is talking about today. But the thing is, given we know these are the solutions, but there are more specific and more detailed questions that we need to answer through energy system analysis. The first one, I think, when we talk about 26 carbon neutrality in China, this means that decarbonization should be done deeply and rapidly. So it's not like 30% reduction in 10 years or 40% reduction in another 30 years. It's about net zero or carbon neutrality in 2016. So which means if a specific technology couldn't be largely applied by that time point, maybe at least at this point, it should be excluded from the current scope of selection. And also, somehow we need more quantified portfolio of technology combination rather than just some qualitative description of technology. Because as I said, we all know we need a combination of those technology. But in specific context, let's say at a national scale, at industry park scale, or at a county scale, or what technologies do we need and how much? Do we need fossil fuel with CCS, or do we need renewable plus storage? These kind of quantified results are important for really guide the realistic transition. And also, I think we need to go from high level model to actionable technology roadmap and project level information. So many models answer questions like, okay, in China, we need to build 10 gigawatt of solar in 2016, maybe. But the problem is how to finish that build or where to build the 10 gigawatt rather than tell people to build 10 gigawatt. I think these are important. Also, there is a link between, we call it macro level and micro level. So when we do the macro models, we need to consider the technology, economic, social, and political dimensions. And when we talk about micro levels, we are facing, companies, products, individuals, and how to bridge the gap. We all know large reduction from fossil fuel is needed from the macro models, but at micro models, how do we incentive the fossil fuel companies to do such transition is another story. So maybe we need to combine these two perspectives. And inspired by such thinking, in the personal net zero America project, we did some kind of preliminary results. So basically, we use a energy system model to project the energy demand service, and then use a pathway model to model the supply side, and then we did some downscaling, basically telling people where to build the energy infrastructure. I will not go to the detail of this method. I want to just show some insights. So basically, I think there are some good or bad ways to use the energy system model. The firstly is we should, as I said, we should understand that the energy system is a complex system, has technical, economic, institutional, and political dimension. And energy system is a quantitative tool in the end. It couldn't fully represent the real world problem in all dimension and all detail. And as a modeler, I think we should acknowledge that, and which means we shouldn't overclaim that our model can explain or can guide things in very detailed level. So I think we should make this clear if we are a modeler. And also, we know some technically pathways, optimized pathway may not be politically feasible. And on the other side, some politically intended pathway may not be supported by realistic technology option. I think here I'll give example as coal GDP is a major government revenue in some place in China. So if we want to do coal phase out or coal retirements, we must put that political dimension into our consideration if we make the solution really feasible. And in other case, we all know renewable penetration is important. It's a politically intended pathway, but in technical, it may be hindered by the not in my backyard issues. So questions like that should be answered. And then I'll give a case study showing how decarbonization of coal power in China are actually there are drivers or barriers for those success or failure. So here I list a real project in China, a real CCS project in China that was designed at a 1 million ton per year CO2 capture and storage. It is designed by a large state-owned company in China, and basically was used for the enhanced oil recovery. So here the interesting is when design, it is a 1 million per year CO2 capture and use pipeline transport and has a budget of 0.8 billion capital cost and the per CO2 capture and storage cost is 300 China yuan. But when finished, the whole thing is different from design. Basically, it only has 0.6 million ton, and the cost really almost triple, and the per ton CO2 are almost double. So then I want to know what are the difference here, or what makes difference here. Again, it is from technical, economic, and social political perspective. In technical, so basically, the energy cost when we compress the CO2 and inject the CO2, the energy cost is much larger than we design or than we do the experimental scale. This is the problem of, from experiment or from lab to reality, which hasn't been figured out. And economically, the land use cost is much larger than thought. And also there are social political, because when you do such project in China concept, you give some hard deadline and you need to finish that by some higher deadline, and then it also increase the cost of the project. So what are the lessons learned here? So basically, I mean, some technologies again may be not as promising, as cheap as they claim especially at engineering projects level. So some people use the word conundrum to call this phenomenon. Basically, if you are a researcher in hydrogen or certain energy, you see, okay, my technology can achieve a certain cost at this level. But this is from a lab scale. In reality, it could be it could be more expensive. Such thing need to be paid attention to. And also benchmarking decarbonization technology has to take multi-dimensional perspective. So I think this is a lesson learned here. So put all this together, IOC, my thoughts on energy system analysis are summarized into 4 points. Firstly, I think filling the gap between top-down and bottom-up model is clearly needed. Playing with scenario has been a standard norm for some time. Could there be better options to address this issue? And we all know our models are wrong. Some of them are useful. So system analysis shouldn't overclaim the usefulness. It's common to say specific technology researchers select specific scenarios to prove the advantage of its own technology. This needs to be avoided. And also, we all know increasing transparency and data availability is important. I can see there are many efforts towards this direction. And also, summarize, I see, understand the multi-skill and multi-dimension feature of future energy system needs interdisciplinary talk and collaboration, like the workshop today. And I'll end my talk with the 2 kind of figures here. This is from JP Morgan's Eye on the Market annual paper. So it's in energy transition, there's basically a war between fossil fuel and renewable. And fossil fuel is a kind of elephant in the room. It's kind of too large to be easily removed from the room. And so this is something we need to pay attention to. And renewable, basically, it's not behave the way you want or we want. So it has its own kind of physical characteristics to run. So we need to better understand and better manipulate or use its features. So with this, I'll end my talk today and hope my talk can inspire some more discussion on this direction. Thanks, Professor Cao. I'll hand over to you. Yeah.
Thank you so much for the interesting talk. I really appreciate your you sharing with us the gap between top-down model and bottom-up model, and also thank you for sharing with us your thoughts on how China could transition its energy system towards a carbon neutral energy system. With that, I would like to ask if there's any question from the audience. You can use the chat, or you can raise your hand if you have any question. If not, if there's no question, maybe we can move on to the let's move on to the second speaker.
Okay.
And we still have some time at the end of the session for questions and open discussion. Okay, so our next speaker is from Shandong University, He-Tong Wang, because Professor Joshua Lee is not able to give us a talk to join us live. So his PhD supervisor is going to present their group study on Professor Lee's behalf. And He-Tong, can you share your screen?
Okay. Thanks to the professors for the introduction. It's my honor to share my research. My name is Wang He-Tong, and I'm from Shandong University. Today, I'll share a paper recently published in the Nature Communications, and the title is China's Electric Vehicle and Climate Ambitions Jeopardized by Surging Critical Material Prices. And I'll explain it in the following 4 aspects. The first part is the background. As the world's largest emitter of carbon dioxide, China has set the goal of reaching carbon neutrality as a national policy to actively address climate change. The automobile industry has become one of the key industries in China's carbon emissions management because of its wide industrial chain radiation, rapid growth of total carbon emissions, and high carbon intensity, which is of great significance to promote the low carbon transition of the upstream and downstream industrial chain and achieve the carbon neutrality in China. In order to promote the low carbon transition of China's road transport industry, China has taken many measures to promote the development of new energy vehicles. According to China's plan, electric vehicles will become the mainstream of the new car sales by 2035, and the passenger cars will be fully electrified. This means that China will remain the world's largest producer and consumer of electric vehicles and batteries in the coming decades. As a result, there will be an increasing demand for the critical materials. However, the recent surge in the critical material prices for the power batteries, such as lithium, cobalt, and nickel, has led to the widespread concern about the competitiveness of the electric vehicles in the near future. For example, nickel prices are volatile in the 2022. On March 8, 2022, nickel prices broke about $100,000 per ton before the London Metal Exchange was forced to step in and suspend trading the following days. This was never happened in the history of the nickel market. Tesla CEO Musk has stressed that the price of critical materials has reached crazy levels, and unless the price is reduced, Tesla may directly into mining and refining on the large scale. However, most projections on the future electric vehicle uptakes assume that the cost of technologies will continue to decrease with the increase of production scale. However, this assumption is prone to the challenge that the price of critical materials needed for the low carbon technologies may surge due to the imbalance of supply and demand in the future. For example, it's widely acknowledged that the cost of lithium battery technology, which has been extensively used in the electric vehicles, would continue to 100,000 kilowatt hour by around 2030. While it is true that the technological innovation and economics of scale will continue to drive down the manufacturing cost of lithium batteries, the material cost of lithium batteries will be mainly driven by the level of scarcity given the limited reserve and the declining overall growth of critical materials, which is currently battery technologies. The Bloomberg New Energy Finance reported that doubling the lithium cost will increase the cost of nickel, cobalt, and manganese battery by 800. Negligence of such important cost factor may lead to the base estimation of China's electric vehicle development in the future, which affects the delivery of the carbon neutral communicate. So this study intends to fill this important niche in the context of China which is to explain to the surge in critical material prices will weaken the market share of electric vehicles in China. The third part is the methods. The research framework consists of extended GCAM stock-driven dynamic material flow analysis model and the life distribution delay forecasting model. We first include the metal price exchange into the battery production price strategy to capture the additional costs to electric vehicles, which will serve as an input for the vehicle stock projection in GCAM. Secondly, we run the GCAM analysis and the material flow analysis to generate results related to electric vehicle market share rate and the corresponding carbon emissions under the material price certain scenarios. Thirdly, we run the lifetime distribution delay forecasting model and the material flow analysis to investigate the material recycling potential. And the material recycling affects the EV cost by reducing the primary demand for these critical materials, which is subject to the volatilities on the international market. These new electric vehicle cost strategies can be fed back to GCAM as a new inputs to reveal the impact of material recycling on the electric vehicle development. The climate scenario we use is a carbon neutrality scenario, and the full electric vehicle cost change scenarios include the baseline scenario, high cost scenario, the medium cost scenario, and the low cost scenario. The final electric vehicle cost chain structured by the combining forms of the cathode material price changes for different lithium battery technologies. The constructed electric vehicle cost chain scenarios and the project carbon neutrality strategies will be entered into the GCAM. In the recycling scenario, we assume that the recycling is closed-looped, namely the recycling minerals reach the quality for battery production. The materials obtained by battery manufacturers through recycling are not affected by the material price fluctuations on the international market. That is, only the primary demand for the materials is affected by the surging material prices. The material recycling potential is calculated according to the material demand under the baseline scenario. And the first analysis of the electric vehicle market share was done through the GCAM. In order to most effectively model the trends in the road transportation in China, we have updated the GCAM 5.2 to include the electric vehicle and fuel cell vehicle technologies for the bus and truck sectors, since the GCAM does not explicitly account for the number of vehicles. It's necessary to convert this demand for transportation service to the number of vehicles, which is done through this formula. Further, we calculated the flow and dimension of electric vehicles by material flow analysis. The third step is to assess the raw material recycling by means of live distribution delay forecasting model. In this model, the total waste stream returning to the recycling term as the sum of direct recycled batteries with batteries from the second use applications and the replacement electric vehicle batteries. The third part is the result. We first model the critical material price change in 3 scenarios. Take the high scenario as an example. We can see the cobalt price has the maximum increment. Lithium prices will continue to rise for the first 15 years, raising about 380% by 2035 before stabilizing the ones with a smaller percentage price increases. In the baseline scenario, the cost of future electric vehicles will continue to fall, largely as a result of the technological innovation. And the electric vehicles in light-duty vehicle sectors will have the higher increase compared to the bus and the truck in the material price surge scenarios. We also analyze the evolution of internal combustion engine vehicles costs as a relative will influence the choice of consumers. The ISIE cost in the material price surge scenario is slightly higher than in the baseline scenario due to the increase in the fuel costs as consumers switch from electric vehicles to ICEV costs will remain relatively stable under all scenarios from 2020 to 2060. The second step is that we model the changes in the vehicle stock. In the baseline scenario, the total projected stock of electric vehicles in China will reach about 36 million units by 2030 and about 550 million units by 2060. The surging price of critical materials scenario will result in the sales to be 2% to 29% lower than in the baseline scenario by 2060. And the increasing cost of electric vehicles make ICEV more economically attractive. As a result, the total inventory of ICEVs will reach 3 to 6 times to the corresponding EV stocks. The third step is that we model the changes in the vehicle market share. In the baseline scenario, the EV market share continues to increase, reaching a plateau of about 31% at around 2045, and then begins to decline moderately between 2055 and 2060 to reach 67% in 2060. Under the material price surge scenarios, EV market share will decrease to 51% to 66% by 2060, which is 1% to 26% lower than the baseline scenario. This leads to a subsequent increase in the market share of ISIE EVs. We also further explored the change in the market share for the EVs equipped with different lithium batteries. For example, in the cobalt-free lithium batteries can only increase ISIE market share by about 5% by 2030 and 3% by 2060. Replacing expensive cobalt with nickel can improve the market competitiveness of the electric vehicles. The first step is that we model the changes in the carbon emissions from the transportation sector. We can see that under the baseline scenario, carbon emissions from road transportation would peak at 0.63 by 2030 and then decline to 0.22 by 2060. The surge in material price scenario will result in peak carbon emissions in the high scenario, being about 10% higher than in the baseline scenario by 2030. And the carbon by the 2060 carbon emissions would be 1.2 to 2.5 times higher than in the baseline scenario. The incremental carbon emissions from the electric vehicles with the titanium lithium batteries are even larger, especially those with high cobalt lithium batteries. If cobalt-free lithium batteries are used, the carbon dioxide will be 3 to 7% lower than by 2030 and 18 to 50% lower by 2060 than in the material price surge scenario. When the electric vehicles are equipped with NCM batteries, cumulative road transport carbon emissions in the material price surge scenarios will be 5 to 28% higher than in the baseline scenario. This means certain material prices for the electric vehicles will put new pressure on China's efforts to reduce carbon emissions from road transportation and could even undermine the achievement of China's carbon neutrality target. Finally, we modeled the road recycling. The recycling potential of materials is on the rise. Due to the delayed effect of materials recycling, the share of recycled materials in the total materials requirement will be only 3 to 18% by the 2030 and could reach 70 to 86% by 2060. Recycled materials reduce the extent to which the materials needed for the electric vehicles are subject to the surging of material prices on the international market, thereby reducing the likelihood of electric vehicles cost peaks. And the lower electric vehicles will increase the electric vehicle market share. By the 2030, material recycling will increase the electric vehicle market share by 1% to 7% in the recycling scenarios. By 2060, even market share could increase to about approach the 67% under the baseline scenario. Due to the positive contribution of the material recycling to the electric vehicle development, the calculated road transportation carbon emissions could decline by 1% to 8% under the recycling scenario compared to the material price surge scenarios. And the fourth part is the policy discussion. We propose several measures to deal with the surge in the price of critical materials. The first is to build a long-term sustainable and resilient supply chain. And the second is to develop the development of alternative battery technology that use large-scale materials. And the third is the cost-effective long-term machines should be established to strengthen the control capacity and the supply management of the critical materials. And the fourth is the shared mobility. Shared mobility may help to elevate the growing demand for the car ownership and use, thereby indirectly reducing the demand for critical materials. Also, this research also bears several limitations. First is the price surge of materials for electric vehicle engines and battery systems could also affect electric vehicle adoption. Second, we do not consider the impact of the phosphorus price change on the electric vehicle adoption. We're considering the adoption of FP batteries given the negligible share of phosphorus in the battery cost. The third is the influence of other factors on the adoption of electric vehicles. For example, the increasing availability and the choice in the electric vehicle models is not analyzed in the study, which should also be paid attention to in the future research. Fourth, this study does not fully capture price linkage between the materials. For example, cobalt price may decrease with the adoption of low cobalt batteries, and the nickel price may increase accordingly, or lithium prices may increase further with the adoption of the cobalt-free LFP batteries. This also needs to be researched in the future. That's all. Thanks for the listening.
All right, thank you so much for sharing your study. I think this is really a unique study, addressing the material price in integrated assessment model. So for the interest of time, we will keep the Q&A session at the end of our session. So let's move on to our next speaker, Professor Li Rong, Dr. Li Rong. Li Rong is now a senior lecturer at Surrey, University of Surrey, and she will talk about integrated assessment model, especially regarding the energy sector. So without further ado, the floor is yours. Please, Li Rong.
Okay, thank you for the introduction. Hi everyone, I'm Li Rong from Center for Environment and Sustainability at the University of Surrey. It is my great pleasure to introduce our research tackling fuel poverty and decarbonization in a distributed heating system through a three-layer whole system approach. Our team also includes Professor Marcel Leach, Dr. Michael Schott, Dr. Mona Chitnis, and three excellent research assistants, Flores, Xiangqi, and Xinyao. And this project is also supported by our partners, which is Working Borough Council, Thamesway Association for Decentralized Energy, UK Energy Research Centre, and National Centre for Energy Systems Integration. Their contribution in terms of data collection and scenario development are very much appreciated. Now let's start with the background. So the direct greenhouse gas emissions in building sector accounts for 17% of the total emissions. To reach the net zero target, the building sector has to eliminate greenhouse gas emissions by transitioning to low carbon heating technologies. And these low carbon technologies are likely to be more expensive than current heating systems. And switching to low carbon heating will impact the lower income household in particular. In 2019, as many as 13.4% of households in the UK were classified as in fuel poverty, and the transition to net zero might accelerate fuel poverty if under improper strategy. So how to minimize fuel poverty in the UK while simultaneously delivering net zero targets is a research question that needs to be answered urgently. And this is an overall of this research. So our project has two main objectives. First, to establish a systematic analysis framework of heating decarbonization to minimize fuel poverty. And second, to perform a case study and propose technological and policy solutions. So on the left side, we can see the key components in this framework. The current available grants are included as a business as usual policy scheme. And besides that, we also introduced no grant scheme and a proposed scheme. The only difference between the proposed and business Euro scheme is that we added the fact grant, which has no funding limits and less eligibility requirements. Buildings with EPC D, E, F, and G are all eligible to apply. For the heating technologies, we consider the air source heat pump, electric boiler, and traditional gas boilers. And in terms of the energy efficiency improvement measures, double glazing, loft, gravity wall, and solid wall insulation are reflected in our study. And then to fully address a few poverty issues, we set 3 economic entities, including the central government, local authority, and household, to review the cost burden shifts among them. And then the middle part is the proposed 3-layer heat flow-on modeling, combining the building stock analysis based on Cambridge housing model, distributed heating system optimization based on mixed integer linear programming, and economic and environmental impact simulation based on environmentally extended input-output analysis. Due to the time limit, I won't go through the details of each layer, but you could find all of the information in our publications. And we also plan to release the work as open source software to maximize the impacts. And for the case study, we selected working a modern town in the heart of Surrey, and especially we focus on the social housing in this project. Next, to briefly introduce how the 3-layer heat flow-on modeling works, we can look at the scenarios and outputs. So besides the basic data, like the parameters of different technologies, energy demand, we paid special attention to these 5 factors to further explore their impacts on the whole system. So as I introduced earlier, we have 3 future policy schemes. And then for the minimum emission reduction target, which is listed as ERT, this is a key constraint in the optimization model. So we run the model by traversing from 0 to 100% with a total of 25 levels. For the projected carbon intensity of grid, which is GCI, we consider the range of 0 to 15 grams of carbon dioxide equivalent per kilowatt hours on the basis of the projection of future GCI in the 6 carbon budget. We also considered the uncertainties of future energy price by running around 20 scenarios on both natural gas prices and electricity prices separately. So in total, we proposed 456,000 scenarios through a full combination of the above factors. And under each scenario, the model provides an optimized combination of heating technologies and insulation measures, the cost of different stakeholders, impacts on various industry sectors, and the impacts on multiple scopes of greenhouse gas emissions for the entire socio-economic system. And also, if we fix some of the factors, for example, under a given ERT, GCI, and future energy prices, the model can compare pros and cons of different policy schemes from both environmental and economic perspectives for different stakeholders. Or under given GCI and future energy prices, the model also functions as a decision-making tool to compare decarbonization plans under different ERTs for each policy scheme for proposing a bespoke heating decarbonization strategy. Now let's move on to the results. So in the next few slides, I will show the results under this scenario, where policy scheme, greenhouse gas emission reduction target, projected carbon intensity of grid, and future energy prices are fixed. And this is the most ambitious scenario and can only be achieved when the carbon intensity of grid is 0. Here we present the optimized selection of heating technologies and the insulation measures. The 1658 social housing are classified into 6 types according to its EPC rating, and the figure in the middle, highlighted by green, shows a selection of heating technologies under the selected scenario. We can see that no boilers will be installed when ERT is 100%, and only air source heat pumps will be installed. Then let's take a look at the cost of different stakeholders. And this slide shows the annualized capital investment from central government, which is a grant shown by red, and from local authority, which is Working Borough Council, which is shown by the pale blue bars, and the extra energy bills paid by household of social housings, which is the dark blue bars. And ours is this small part highlighted in green again. And under the business as usual policy scheme, the existing grants are only contribute to very limited proportion of capital investment. And most of the capital investment are undertaken by local authority. Household will pay extra energy bills induced by the heating system decarbonization, which is about 340 per household on average. And now let's try to expand our analysis to the industrial system. And this figure shows the changes in total output and direct greenhouse gas emissions of different sectors compared with a baseline scenario. So with less gas boilers, the total output of gas sector decreases as expected. And meanwhile, the heating decarbonization brings about strong increases in electric equipment, electricity, and construction sectors. It would also stimulate the economy to various extents among other sectors. The direct greenhouse gas emission trends, which shown in the right-hand figure, are quite similar to changes in total output, but different responses could be observed as for various emission factors. For example, in this extreme scenario, when the GCI is zero, the electricity sector contributes to the majority of industrial greenhouse gas emission reduction, even under increased total output. And then let's further expand our analysis system to the whole economy. And in our study, we define the whole system greenhouse gas emission as the sum of emissions from household gas consumption and total greenhouse gas emissions of the industry system. And then the three columns highlighted here will be the results of the selected scenario. So we can see that comparing with the greenhouse gas emission reduction of industry system, the greenhouse gas emission reduction caused by natural gas consumption of household is much lower. And this further illustrates the importance of considering the environmental impacts of the whole system. Now, I hope you all get a sense of the functions of our heatful modeling. So I would like to share some interesting results based on some sensitivity analysis. And this slide is about the emission reduction target, and these two figures display the differences of annualized household energy bills between different policy schemes, as GCI falls from 15 to 0 and ERT decreases from 100% to 0%. The left figure is a comparison between no grant scheme and business as usual scheme, and then the right figure is the differences between business as usual scheme and the proposed policy scheme. So when ERT is close to the upper limit of the emission reduction, the proposed policy scheme provides a best plan for households, followed by business as usual scheme and no grant scheme. But as ERT gets lower, no continuous pattern can be obtained. And this is partly related with the nature of the optimization model and might be also related with our simplified and rough design of the policy supports. The last section is conclusion and future work. So in general, we developed the three-layer heatful modeling that could determine optimal technologies and policies to ensure a just transition. And we also hope the case study of Woking could shed light on other regions in the UK when proposing strategies to tackle food poverty. And our team will continue our research in this area. In the short term, we will focus on the technology and policy perspective to add more advanced heating technologies in this framework, such as hydrogen, and to design and simulate more sophisticated and practical policies to inform decision-making. And that's all from my presentation. I'm happy to take any questions. I will stop sharing now.
Thank you, Nero, and thank you so much for your passionate, presentation. Also, thank you so much for sharing, the recent progress of your project. I think for the interest of time, we will keep, the Q&A in our preliminary discussion. So.
Okay.
All right. Okay. Now let's move on to our next presenter. From Peking University, Professor Han Dai. So I think there's no need to introduce, Han Dai, since Professor Dai has been, a prominent researcher in our field, especially in the field of, integrated assessment model. So without further ado, the floor is yours. Please, Professor Dai, can you share your screen?
I try to share my screen and
Sure.
or yeah, Professor Hall, can you because have some problem maybe with my device, so I send you my
Sure,
slides
sure.
and you share it with me okay?
No problem. Yeah, sure.
Okay, 1 minute. Okay, so can you receive my slides?
Yes, the slides come over, so just give me 1 sec. Okay.
Yeah. Okay.
All right. I'm gonna share my screen and let me know if you can see my screen or not, okay? Can you see my screen?
Yeah.
All right.
Sure, yes, I can see.
Okay.
So good evening and also good afternoon, everybody. So this is Han Dai from Peking University, and I'm very glad to be here to involve with you some work in my group or in our community on the integrated assessment model. And so maybe we can also think how we can connect to each other with our database, our model, and our teams. Okay, so my talk is about integrated assessment of the multidimensional impacts of climate and environmental policies. So next, and very briefly, so next， 你可以下一张吗？好。Our next slide. So before that, so our modeling, we are facing, sorry, the second slide, facing a, can you go to the previous slide? Slide two.
Yes, I already switched to slides 2, yeah.
Okay, so this is slide 3. Yeah, this one. So our modeling, before we model and we find solutions to how we can transit to any sustainable future or low carbon world. So we have to keep in mind that our social economic system is in a very complex interactions with the natural systems, which are including the water resource, energy, climate, and also other land use systems, and also all these systems are subject to quite dynamic change in the short and the long term. So in our simulation, our modeling, our policy assessment, we have to try to keep all these factors in our toolbox. And so it becomes quite complex. And then, can we go next? So so we have to transform different kind of systems toward. Sorry, 下一张好吗? Next. Transform different systems toward the previous. Okay, sorry, previous slides. Slide 3. Yeah, this one. So what we want to bend the curve from the unsustainable future to some target-seeking scenario, as we can see here in the circle of the different SDGs. So of course we have different pathway, we have different solutions that can lead there. So, but in the problem behind it is that under each pathway, we have to know their cost and benefit. their synergies and trade-offs to different other dimensions. So in order to find the most appropriate, a relatively most appropriate pathway that is feasible, that is cost-effective, and this is which is low risk, and so on. So all this kind of study need to try to understand what is the potential impact or multi-dimensional impact of different policies, different pathways on other aspects. So okay, next slide, slide 4. So yes, so I mean, yeah, and also click again. So all this kind of things, we need to know the interaction between our policy in the left-hand side of the box. Either it is a industry structure change, or energy structure change, or transportation change, and so on. So we have to know the potential impact or multi-dimensional impact, including the economic impact, social impact, resource impact, and environmental impact of the left-hand side pathways, and to see if those impacts exceed the boundary of any of the right-hand side system. For example, talking about the industry ecology, so some energy solution of like a renewable energy solution may be feasible in terms of carbon reduction, but may be infeasible in terms of the resource demand requirements, like the critical minerals, right? Like looking at the supply chain, so maybe they are infeasible. So of course, this is only part of those assessment, but we also have to look at employment implication and also other environmental co-benefit or environmental trade-offs. So this kind of thing, in one word, we need integrated assessment to help us to know those kind of the things. So next slide. Yeah. So in this field, we have some big modeling giants all around the world, including the US, and some of 3 of them or 4 of them are in most of them are in the European Union, and also some of the teams are from Japan. So also in China, so we are kind of emerging community. So there are many young or traditional modeling teams active in this field, and our team is just one of them. So we hope that, yeah, and I also think that the big giants, they have made very big contribution to the 6 rounds of IPCC climate assessment report, and also we are now in the 7th cycling. And I think in the next phase, we should build the bridge or build some connection between the integrated assessment community with the industry ecology teams, like as we are here, because the key issue of some shortcoming of those big models is that it's good at capture the whole system interaction, but if you look at some detailed process, detailed sectoral and technological feasibility, then it cannot answer very well those kind of issues. But instead, I think the industry ecology community and the database, the method, and also the insights can help us. It's a very, very ideal complement to our community. So next slide. So yeah, and then several slides, just to talk briefly about our work in our team. So we established or developed our own integrated assessment model. So this is the IMAD model in our at Peking University. So it covers different modules, like as shown here. Some of them are economic model, like a CGE model. So I myself is traditionally work intensively with CGE model, so global model, provincial model, national model, and so on. In the meantime, we also develop our own bottom-up type technology model, which is focusing on energy system analysis and optimization. And also we have coupled this kind of energy economic integrated assessment model with environmental and health model, air quality model. And in recent years, some of our PhD students are trying to link the big models with the material flow analysis and other resource input and output databases. So in order to answer the still unclear questions of different transformation pathways and so on. So our ultimate goal is to compare the cost and benefit, compare the synergy and trade-off, compare to see the feasible solution and cost-effective solution on the right-hand side, on our right-hand side, and so we can find an optimal policy pathway in the left. So next one, yeah, just very briefly again. Next slide. So we just pick up several, big, short work based on our existing work. So for example, this work is based on our IMAT CGE model. We capture the carbon and water synergies and risks, of course. So published last year. So the key issue is that in the panel A, so we can see that as the national and provincial carbon emissions reduce to different extent, so the simultaneous effect shown in panel B is that the industrial water use can be reduced simultaneously. And good signal is that as a whole, nationally, we can achieving carbon neutrality could enable China to attain its industry water use target, as the title here show. But we also, if you look at the provincial detail or the sectoral detail, so we can see that not all provinces can achieve that goal, water use goal. So in other words, yes, we did see some synergy, but still, carbon neutrality is not enough. Alone is not enough. We have to also there are some trade-off that there's some water leakage from one sector to another sector, from one region to another region due to carbon reduction. So some trade-off would also happen. So that is one message. The next slide, where we can also show that looking at the rural energy transition, so we can also see that in order to achieve carbon neutrality, so rural energy sector, or rural energy consumption, especially the rural scattered coal and traditional biomass energy, should be largely replaced with modern energy and clean energy. So, and also we see it is highly cost effective, and in most provinces. And then simultaneously we can achieve a clean air target and also a substantial amount of health benefit. So that, but each province, they have their own priority in terms of the technology mix and so on. So that is the second paper. And next slide shows another recent study published this year. So we looked at the food system and land use system, and then tackled the energy, carbon, and the food nexus. And the key message is that, okay, China may, of course, we need some, we have some carbon sink from the terrestrial ecosystem. But this study, we looked at the negative emissions that could be provided by large-scale bioenergy with carbon capture and storage technology. That can provide another big amount of negative emission potential comparable to the carbon sink. But we also know that it could endanger China's food security or transferred environmental burden to the trading partners of China. So the whole piece of this work is to find an optimal way that will not endanger China's domestic food security or increasing the environmental burden of our food trading partner, like in Australia and in Brazil and other regions. So we find a solution space for achieving the triple goals of carbon neutrality and bioenergy expansion and also sustainability globally. So that is this work. And the next slide, yeah, we also in this modeling community, we also organized some training workshop. Like in this August, we also hosted one national workshop from weekends. Here we also organize activities to apply to communicate with us. And the next slide, we also show that I have to say that in this area quite new and quite next slide, yeah, not very much especially not very much Chinese scholars. They're more dominated by the IPCC cycle and the big teams. So I think more and more younger researchers or young students are welcome to join this community. And also, yeah, especially in the next round, the AR7 round is very much needed. And yeah, next slide. So I also invite you that I'm very glad to, as a team representative of our team, I'm very glad to interact with you. And also, yeah, also you are welcome to contact me or any of my colleagues, team members to do some potential collaboration. So that's basically all. Thank you so much. Yeah.
All right. Thank you so much. Thank you, Professor Dai, for sharing with us your recent progress, and especially the three important publications from your recent work. And I know that you have a very busy schedule. So since you are not able to join us, in our plenary discussion, but I'm hoping that in the future we still among the five speakers, also among the audience, you will be able to have more interactions with us. Okay, and thank you so much, Han Dai. So now let's move on to our last speaker, Professor Zhao Hui. Wait, I'm gonna have to stop sharing. Okay, our last speaker is Xiaohui Zhang from Beihang University, and also he's also now research scholar at ISIE. And Xiaohui Zhang, Professor Xiaohui Zhang will share with us, his recent work on air quality co-benefit of carbon neutrality action in China. The floor is yours, Professor Zhang.
Okay, thank you. Good morning, good evening, and I'm Xiaohui, currently working at the ISIE and Beihang University. Today, I would like to share some insights from my recent work regarding the air quality co-benefit of carbon zero in China based on the different modeling assessment. And And actually, firstly, I would like to show the background. As already know, the climate change is a big problem for us across the globe, not only for China. And we also try to limit the global temperature within 1.5 degree, but at the same time, sometimes we don't know how can we achieve the carbon zero or limiting the global temperature within 1.5 degree. And even if this kind of pathways are clear, or we still need narrow thinking, or there's have some thinking regarding if some carbon zero actions are implemented in the future, such action might have positive or negative impacts on air pollution as well as the air quality and health related to air pollution. And what I want to say here is that in the future, for example, in China, there might have many different pathways to achieving carbon zero targets across regions, across sectors. And if the different actions are selected, the impact of air pollution are very widely. And we still not clear whether if we only considering the carbon zero action, could we achieve the air quality standard based on the WHO requirements? And if not, whether they have extra actions to further decline the air pollution or improve our air quality. And today, one model I would like to introduce here is the GAINS model. And what's GAINS is that in the GAINS, we are trying to focusing on analyze the relations and the synergies between greenhouse gas and air pollution. And for the GAINS, what we need is that we need the activity like the energy use by sectors, by fields. We also need the industrial process. We need the agriculture part, we also need the transportation. And within the gains, we covered over 2,000 air pollution control technologies that will be used to analyze whether currently or in the future there have some potential to decline the air pollutants and what costs are needed. And after that, we also considering integrating the air quality model to further analyze the health impacts as well as some ecosystem impacts due to some action that implemented maybe from the energy side or from the air pollution side. Currently, the GAINS model is publicly available for Europe, for Asia, and for the IAM model. The IAM, against IAM means that this model will allow you to analyze if the IAM model achieving and analyze the carbon zero pathway, whether such action have some impact on air pollution side. And it's mostly aiming to used in the IPCC AR7 report. And for the Asia, that including China is the provincial level, including Japan, India, and Korea is their regional level. Actually, within IASA, that also have some the other restricted version of the GAINS, like the GAINS Global, that only available for some collaborators, and we also have some national model like GAINS Korea with more detailed region and GAINS South Africa, as well as GAINS IGP in India. And indeed, for the gains, we also have the optimization analysis to figure out in the future what cost-effective actions can be used to achieve the default air quality targets. And currently, we also extending the gains model for further pollutants or further greenhouse gas like the methane, like F gases, like the mercury that are very important to further expanding analysis the synergies between greenhouse gas and the air pollutants. And indeed, the air pollution is not the regional problem. Sometimes it's the city problem. So that's why in the GAINS model, we also developing the GAINS city, like the GAINS Tianjin for 28 cities, like the GAINS city for Hanoi. And like I mentioned earlier, we developed the GAINS AR6 and the GAINS AR7 that using the models from IAM to GAINS to further analyze if different pathways are adapted across the global and what air pollutant will be there and what potential can be achieved under their carbon mitigation actions. And actually, we also developing the plugins model to further analyze and further use the gains to increasing the efficiency, like the scenario analysis, like how to efficiently to deal with the data, because for the gains, there have made over a million of the data for each region, and how to quickly to look at the results using the plugins. And at the same time, we also try to thinking how to extend the gains model in the short term and in the long term. For example, in the future, we will further improvement of the waste in the gains to figure out if the circular economy are further considered to decline the CO2, to decline the materials, what air pollution will be declined due to the circular efforts. And currently in the gains, we are always using the optimization model to identify the cost-effective manner under the defined targets. The targets might be relevant with the health of air pollution. The target might be relevant with the ozone, also sometimes relevant with the greenhouse gas target to further analyze the integrated measures to achieve the defined targets with cost-effective approach. And currently, like I mentioned, that gains is cover the air pollutant, also cover the greenhouse gas. Here we show the metrics regarding the relations between the air pollution and the impacts, that including the health impacts, like the climate impacts between the air pollution and the greenhouse gas. For example, I don't want to extending this matrix, but I want to give one example is that regarding the health impact related to PM, that relevant with the pollutant like the primary PM, also some secondary PM or that caused by SO2, NOx, VOC, and ammonia. And sometimes in the gains, as I mentioned, because that including all of air pollutant and the greenhouse gas, we also try to analyze the trade-off and the synergies. For example, it here, if give the plus single, it means that between the CO2 and the pollutant have the positive co-benefits. And if they have plus and the negative, it means that for some pollutant with these impacts that are including both positive and trade-off. And it here, I would like to show the recent work regarding how can we linking the IM model, like Professor Dai mentioned, that including like messaging, like the like Professor Dai's model, also like the GCAM, like the IEA's model. And how can we link this kind of model into the gains to further analyze? It here, we should firstly to pick up some information from such integrated assessment models that including the activity of energy part, including the activity of transportation, the industry, the agriculture, and waste. As I mentioned in the gains, we already including the waste part. For one thing like the energy, we should considering like the fuel consumption for each energy sector, and also the related process of industrial products. And once we importing this kind of activities into the gains, we can further using the gain to analyze the emissions based on the embedded information of emission factor, based on the cost elements or control strategy of air pollution, as well as some further air pollution policies. Like if we are adapt some clean air policy in the future, whether they have some further reduction of air pollution. Indeed, after that, we also can using the air pollution model that currently have in the gains to further analyze the air quality changes under different scenario and different action. Currently, the resolution of the concentration is 0.1 by 0.1 degree. It's around 10 by 10 kilometers. And we also distinguish the source from urban and rural, from low and high of transportation sector. And as I mentioned that in the gains, we also including the impacts part that are consistent with the GBD's IER module, the health impact assessment model. And we can also using this manual of the gain to analyze the health effect of air pollution. And as I mentioned, how can we import the IAM data into the gains? Here I just show one example what data are mandatory if we want to build a linkage between IAM model and the gains, like between message and gains, between IMAD of gains. So we need the final energy of each sector by different fields. That sector and field will linking with the gains field and the gains sector. And at the same time, we also need the storyline. For example, if we have the baseline of IAM scenario, we should linking the SP2 and considering the air pollution by current legislation. And for the agriculture, maybe we also thinking we need considering the baseline rather than the others. For the shaping, the international shaping, we need using the theory, the baseline. And sometimes if we want to say, if I want to linking the carbon zero scenario into the gains, we need to select the SP1 1.9 degree that are consistent with the IM model. Here, if we assume we are linking with 1.5 degree, we should further consider the air pollution control strategy with MFR. The MFR means that all maximum technology will be used. Such technology are already implemented in some regions in the games, but not all regions. There have some potential to further use to achieve the air pollution abatement with the technology feasible potential. And maybe for the agriculture part, there have some further assumption like efficiency of nitrogen use or the health data to decline the food, decline the animals, or something like that. We should further consider all of this information before importing the IM scenario into the games. And in the following slides, I would like to show the draft result, what I did based on the GCAM provincial model, based on the Message China national model Arcunia scenario, based on the IEA's carbon zero scenario. Here, I just show the energy used by key sectors at the national level, because GCAM model is a provincial one, Message is a national one, and IEA is a national one. And at the national scale, we can easily to compare what's the difference under the same target like carbon zero. So we can see they still have slight difference. The GCAM always have higher energy consumption by sector, but if we look at the fuel use across these three models, we can easily find the largely difference of the coal consumption, the coal contribution of the system. And it means that even if they have some more energy consumption in GCAM, they might be have less coal consumption. It will using more renewable energy. And follow that, we also to figure out under the carbon zero pathway, what targets is there. We can easily find the message and the IEA are with using the lowest carbon mitigation targets, because these targets are under the global analysis within 1.5 degree. But for the GCAM, the GCAM assume is the carbon zero carbon neutrality for China. They have very, very limited consideration of the other regions of global. So that's one difference. And if we are talking about the air pollution, here I show two things. The air pollution only considering the carbon mitigation measures and what could happen for the PM2.5 emission reductions. And if we further considering the best availability of air pollution control technology, what could happen of the maximum of reduction for PM2.5. You can see they still have large difference, but not so much, especially for the 2050. And if we are talking about NOx, SO2 is similar, but if we look at the NOx, we can find also similar, but for the ammonia, we can easily find between 2020 and 2050. They still have large difference. And for different models, the ammonia consumption are very widely at the national level due to the activity difference of agriculture part. And indeed, I also want to further analyze like the air pollution concentration, especially for PM2.5. You can see it's terrible for us by 2020 compared to the WHO standard. And if we say by 2050, after the different scenario, what could happen under the carbon mitigation actions for messaging, we already can find by 2050, there have large improvements across China, especially for Tianjin from dark red to the light red. And for the GCAM, it's similar, but on the provincial, on the concentration distribution, the GCAM have further improvements, especially for Tianjin and the middle of China. But if we're talking about IEA that are consistent with the message, because both models are national projection, but for GCAM, it's provincial projection that are different. And if we further consider the air pollution control technologies, we can see the air pollution, the PM 2.5 concentration improve a lot. Most of the regions can achieve the WHO targets, like around 10. Here, there's still, like this one, there's still higher place of the concentration due to considering the natural source, like the dust in Inner Mongolia that are considered during the study period. And last, I would like to summarize what I showed it here. Firstly, we're linking different IAM model with the gains to analyze the co-benefits. Maybe the trade-off is there, but due to the time limitation, I just want to show the co-benefits between air pollution, between the CO2, as well as air quality improvements, and the different carbon zero pathway. And based on the results, we can easily find by 2050, most regions can improve the air quality, but it's still high if we only consider the carbon zero actions. It means that we should further consider the air pollution control combined with the carbon zero actions and find the most cost-effective approach. At the same time, we also need to thinking how to improve our resolution of current IIM model. Like Professor Chen Dai's work, the IMAD is the provincial level, that's really great, but for the GCAM is the provincial level, it seems that's great. We can further analyze province by province, give more occurrency analysis. But for the messaging, for the IEA, it's a national model. It may, on their side, maybe in the future, they need to further improve the resolution, the spatial resolution of their model. And at the same time, what I want to say is that if we further consider the air pollution control measures in China for most of the regions, we can achieve the WHO air quality target for 10 or even 5 microgram per kilometer that can help us to improve our health as well as due to the air quality improvements. That's all. Thank you.
All right. Thank you so much, Professor Jiang, for sharing with us, your recent work. I really appreciate, appreciate that you share with us the recent work, from your GANS model. I think this is really, really amazing work. But due to, for the interest of time, I think we should move on to our last part of our session. So, of course, if there's any question from the audience, please drop your question, in the chat. I will try my best to get to your question during the plenary discussion. But before I get to individual questions, I would like to I would like to, have a broad discussion about what we have learned, from the 5 great presentations, and also what we can take away, from the 5 presentation. And most importantly, I think, is that what we should do differently moving forward. As we all know, integrated energy and environmental system models are very, very powerful tools for us to explore the solution space, the so-called solution space, by describing a wide range of possible pathways that can help us achieve long-term policy goals. For example, global climate change, mitigation objectives, and also at the same time highlight the potential feedbacks and also trade-offs between different choices regarding the energy system, economic system, and environmental system. And I would like to, structure my question into 2 parts. The first thing is, what we have learned or what we can take away, from our 5, great presentations, and also the secondly, how we can do differently if we want to move forward. So my first set of questions, or my first couple of questions are directed to Professor Li Rong and Chuang, since the two of you have been talking a lot about bottom up insight also, and how important the bottom up insight is. I'm just wondering, first, if given the opportunity, how would you like to incorporate, bottom-up insight into integrated assessment model? Because the two of you have been talking about this bottom-up insight, and the other three speakers, they are, they talk more about this global level, big integrated assessment model. But according to what you have shared, I think the two of you are more familiar with this bottom-up insight. So I want to ask you, how would you like to incorporate bottom-up insights or bottom-up engineering insight into integrated assessment model? And also the second question is, in incorporating this bottom-up insight, which bottom-up insight do you find most important, for improving the accuracy, also the comprehensiveness of integrated assessment model? Li Rong or Chuang, you can, either of you can go first.
Yes, maybe I can make a start. So I think it is really important to incorporate bottom-up model with the top-down models, or maybe using bottom-up model as part of the integrated assessment model. Because like most of the top-down models or the whole system integration, or whole system assessment model, we're looking at the whole pictures. Well, this can be very helpful, provide us lots of, large pictures inside, but the shortcomings of this kind of model is loss of details. And that is an opportunity where we can incorporate bottom-up models to reflect the engineering details, or maybe using some physics knowledge supported information to bring more insights into the whole system. And if I continue use my example of the heat-for-all model in my presentation, and for this three-layer heat-for-all modeling, actually the first layer, which is based on the Cambridge housing model, is a bottom-up modeling. So the first thing we need to do is to extract the data from the English housing survey to gather the data on housing data. This might be some demographic information, and also the environmental data, which reflect the outdoor environment, and also some physics characteristics of the building itself. And by doing this, we can have better or accurate estimation on the energy demand, both before and after the retrofit. And I think comparing with the traditional way, where we maybe make some assumptions or just extract some predictions on energy demand, I think this will definitely improve the accuracy. In general, I think my understanding of how we can better incorporate these two kinds of model is to try to find the common parameters, or maybe some shared decision variables, and that will be the key part to incorporation. But in terms of which part of data or which part of information is the most important, I think that must be case by case. Well, for my case, it will be better estimation on energy demand. But maybe for other models, the answer will be different. But overall, I think this hybrid approach is a really better way to forward. Yeah,
thank you so much. Thanks so much, Li Rong. I think I totally agree with you that the integrated, the convention, not a conventional, let's say the state of art integrated assessment model has have been criticized for using really simple assumptions on demand sectors, like how much heat is demanded by the residential sector, and it is very important to have a better understanding of the physical characteristics of the residential sector by looking into the physical dimension of the residential sector, also maybe other important social economic dimensions. I totally agree with you that we should have this bottom-up insight integrated into our integrated assessment model, and also it's definitely case by case, because we have so many sectors, and each sector has its own, characteristics. We need more bottom-up insight from each sector. And thank you so much for sharing your thoughts with me. And maybe Tran, could you share with us some of your thoughts?
Okay, so thanks for the excellent comment, Leo, and how. So I fully agree with what you have said. So basically, if we want to integrate the two kind of model paradigm or two model norms, it's a case-dependent thing. But I also want to emphasize that we shouldn't, let's say, do the integration just for integration, that means in sometimes different models are designed for answering different kind of questions. If we or in other words, we couldn't answer all the question in one very complicated or very integrated model, or maybe it's not a good way to go forward if we want to play the Lego game. We put all the modelers in one very complicated model. Why not just leave some models over there and saying, if we want to answer question A, we use model A, and if we want to answer question B, we use model B. And sometimes there can be, conflicting insights from different models, and then we try to explain. So this is my first input to the question. And the second in question, if we want to do the integration, what information is let's say, is the most important? Because I do a lot of energy structure or energy future energy mix prediction or projection, that kind of thing. I think if you look at the the basic logic or the energy system model, the basic logic is kind of least optimization, least cost optimization. So basically, it simply deploy, or it simply use the least expensive or the cheapest technology. So in that case, I think, of course, the cost information, the capital, the operation and maintenance costs are key information that we need to carefully play with. If we kind of basically in some ways we can manipulate the model to produce whatever result we want if we give them different cost information. So we need to use a transparent way to show that cost information, and to really demonstrate or prove our cost projection are solid. I think this is one key point. I think we should make it clear. That's all from my side. Yeah.
Yeah, I thank you so much for sharing a different perspective on, or do we need to, integrate all bottom-up insight into integrated assessment model? I totally agree with you that it's not necessary, or let's say it is not possible or feasible to integrate it, integrate all bottom-up insights because it's simply too complex to have all important insight. But I would like to follow up on your second thought regarding the cost information. So you basically suggest that we should incorporate cost information, at least real world cost information, into integrated assessment model. But I'm just wondering how we could do so. What kind of bottom up cost information we should look into?
Yeah, I think that's a good question. It's a challenge. The problem is in models, many technologies we are talking are actually hasn't been, fully deployed or fully demonstrated in industry scale. For example, we talk about hydrogen, but in reality, the industry scale hydrogen projects are very small. There are few projects, so it's hard to derive their real cost. So I think there is a kind of from lab to industry, or from 0 to 1, and from 1 to n. And we have first of its kind, and then have its end to ends of its kind. And how do we use a set of method to mimic the change of such, you know, a skill up or the challenge of, you know, from 1 to n. It's clearly important, but honestly, I don't have you know, clear answer from my side for now. But I think that's the perspective. Yeah.
I see. So I think it's already, you know, good enough to, you know, already identify where the, you know, the question is. I think this will require, you know, more effort from the community, from, you know, from the audience, also from other communities beyond, you know, the industrial ecology community, and also the IAM community. Right. I thank you so much for sharing with us your thoughts on, you know, on this set of questions. And then I would like to move on to, you know, to other speakers regarding, you know, because the next set of questions are, you know, targeted at Professor Xiaohui Zhang, because Xiaohui, you have been talking a lot about, you know, the potential trade-offs between energy and environmental policy objectives, or maybe it's called benefit. It doesn't have to be, you know, trade-offs. It could be called benefits. I'm just wondering, could you help us summarize, you know, because you already shared a lot of insight, you know, through your slides, but just would like to ask you to, you know, summarize how can integrated assessment model help us, you know, address the potential cost benefits or the potential trade-offs between energy and environmental policy objectives, and you know, or if you, I know this is something you have been working on recently, but do you have do you have anything else you would like to share us, or something you plan to work on, you know, to address the potential cost benefit and the trade-off between energy and environmental policy objectives?
Yeah, so actually from my side, I can show some experience that I did a few years ago and also recently that published with a colleague. One example is that in China, the Chinese government announced and implemented the 3-year action plan to control the air pollution. The action of 3-year action plan not only focusing on the air pollution control by end-of-pipe technologies. And actually, they also have some measures or action that relevant with air pollution control, also relevant with the CO2, like the fuel substitution in the heating in Tianjin. The Chinese government would like to say we would like to using electricity and gas to replace the coal to decline the air pollutants. That belongs to the 3-year action plan. But indeed, if they decline the coal is the common source for the greenhouse gas emission, the source of air pollutants. If the coal are declined at the same time, they have the benefits not only for air pollution abatement, they also have some extra benefits for the CO2 reductions due to this action. And another example is that also might be within the 3-year action plan, the Chinese government mentioned in the industrial sectors, we should phasing out some, also for the power sector, we should phasing out some small scale of the capacity enterprise or the company. And this action can improve the energy efficiency in the sectors. And such efficiency improvement also can decline some fuel use and produce the same amount of products. And that also can decline the CO2 and air pollutant at the same time. But what I want to say, not only for the co-benefit, we can say this is cost-benefit. There also have some trade-offs that I would like to figure out. For example, in the future, if we want to achieve carbon zero targets across China, there might be have some coal power plant with CCS. And the CCS can decline the CO2 emissions, but the CCS technology will consume extra energy, might be the electricity from coal power plant. It means that we will have extra fuel use related to the coal, but such extra fuels will emit air pollutants. This is a trade-off. They have the benefits only for CO2, but they will increasing a little bit of the air pollutants. If the policymakers want to set such policies, such CCS policies, whether they also need to consider the air pollution standard in the regions. If not, maybe the air quality will be terrible in the future, even if they can achieve the carbon targets. And so finally, I would like to say maybe on the policy side, if we want to provide some policy recommendations, we should considering the co-benefits and the trade-offs. Yeah, that's what I want to say here.
Okay, thank you so much for sharing us, your thoughts on the potential benefit and also trade-offs, between different policy objectives. And I believe, integrated assessment model, will do a lot, in this domain, especially addressing, the potential benefit and trade-offs, because this is exactly what, integrated assessment model can do, right? So, all right. So, I would like to move on, to our next speaker, Hetong Wang, because Hetong, your research, is looking at different aspects of integrated assessment model. Because, for example, Li Rong and Chuan, they have been talking a lot about the energy system models, addressing, the energy transition, also the energy poverty, and Professor Han Chen-Dai and Xiaohui Zhang, they have been looking into, the trade-offs between the co-benefit or trade-off between different policy objectives. But I think your research is a little bit different from, from the other speakers, because you are looking at the material dimension of the whole, of the energy system. So I'm just wondering, what I mean, in addition to this material, dimension, I'm just wondering what additional critical elements or aspects you believe are still missing, in integrated assessment model, and and also, what strategies would you propose for, refining the state-of-art integrated assessment models, moving, forward? Hetong, are you with us? Yes.
Okay. I think the metals are the potential bottlenecks for the energy transition. The current integrated assessment models do not include the critical role of these metals as inputs, and the potential rise in the cost due to the energy transition. Including metals as an input in the production of renewable energies and batteries may capture this additional cost and help us to better understand the impact of energy transition on the fluctuation. Future research should try to incorporate metal models into the integrated assessment model at the source, especially not just the price. That's all.
Okay, I'm just wondering. So, because your research has addressed, lithium. Lithium is, a metal, a metal critical for the electrical vehicle, right? I'm just wondering what additional materials, you find important for the energy transition, also for the carbon neutrality transition, in addition to lithium. Do you have any other materials you want to study? Hello, can you hear me, Hetong? I think you're muted. Hetong, you're muted. You have to unmute yourself. All right. I don't know. Maybe the connection is bad, but I would like to open, the floor to all of our speakers. So, our last question is for all speakers. So I think we in today's session we have talked a lot about integrated assessment model, addressing different topics like energy poverty, air quality, critical material, and also water energy nexus. So I'm just wondering, since we, as we can see, integrated assessment model are really, really powerful, tools for addressing or exploring the solution space, right? So I'm just wondering, so how but at the same time, the integrated system model have been criticized for it's difficult to use and also it's difficult to interpret, right? So I'm just wondering, how can we improve the use and also the interpretation of our model results, generated by integrated assessment model, and also I learned that recently the integrated assessment model community has initiated open sourcing initiatives. So what is your take on open sourcing? Can open sourcing of integrated assessment model can help or can improve the use and interpretation of integrated assessment model? Yeah, so my question is basically, first, how do we improve the use and interpretation of integrated assessment model? And second, do you think open sourcing is a good idea, to help us improve the use and the interpretation of IAMs? The floor is yours.
Yeah, maybe I can say something. As
Sure.
the first speaker, yeah, actually for my slides, I also mentioned for my presentation, I also mentioned that in the games we have some public available of the model that can be used by anyone if they want. And actually, if some people access the games model, they have the resource manual to show the material regarding the games, like the guidebook, like tutorials, and that will introduce how to using the model. At the same time, at the other side, we also provide the training of the model. And if some people are interested, they can directly to access the training, there have some video record to introduce what features and if some people want to create the new scenario to give more policy assessment, how can we using the model? Yeah. So maybe in the future, the other integrated models can make it publicly available for all people, and many people can use it freely and something. Yeah.
So I would like to follow up on the open sourcing, since you mentioned that there are initiatives going on, right, to improve the transparency, to improve the availability of GANs. But I'm just wondering why our integrated assessment model are still not, let's say, widely used by the other community, like community beyond integrated assessment model community. What are the key barriers, to increasing the use of integrated assessment model? So could you share your take on this?
Yeah, so actually for games as an example, that already have more than 1,000 users to use the model, not only for the other side, also for China, I can imagine that over 200 people to using this model. And yeah, for the barriers, I would like to say, sometimes for the games, we cover almost everything related to the air pollution. No people can track the latest technology for all sectors, for all regions. Maybe one of them only focusing on like the waste part, only focusing on the power sector, or only focusing on the industrial part. It's okay. They can doing the scenario analysis based on the model with the concerned sectors, but still they need to spend the time to understand what's the philosophy of the model and what the knowledge are required before using the model. I mean, the knowledge is regarding the regional difference of the sectors, the development status, and the future directions, as well as the emission standards. Yeah, maybe that's one barrier, but I don't want to say this is a barrier, because as a researcher, if the researcher want to do the works, they should have the relevant knowledge.
I see. I agree with you.
Yeah.
And thank you so much for sharing, your take on this topic. And I also would like to hear from, other speakers. Yeah,
Okay,
please.
so I can go. So basically, if you let me answer why the IM is not used by other community or by an increasing number of people, I think the reason is very simple, because it's not easy to get started. I personally tried some IM myself. Even, I mean, I wouldn't claim myself as a professional in this region, but I know some basic stuff, but still it's not easy to to actually run some case study or run some scenarios. So in that case, I mean, if possible, I would suggest the community could develop some user interface or some I don't know, kind of graphical user interface to actually make more people can play with it. And actually, if just for most users, they don't need to know the fundamental logic or fundamental physics behind it. They just want to run the model, produce some result, and then see whether it is good or can produce some kind of guideline for them. In that aspect, I would say that could be one direction. And on the other direction, for the real professionals in the community, open source is really needed. And I don't know, for energy system community, there is a kind of intermodal comparison. In Stanford, there is an energy modeling forum. They actually compare even from naming convention to the codes or the structure to show people how different models are actually using the solve the problem in different ways. So we can try to promote such practice in the community a bit for the professionals. So in summary, I suggest two ways to go. For general users, develop some kind of user-friendly interface to get people get started. And for the professional, use open model practice and to do some intermodal comparison. This is what my suggestion. Yeah, thank you.
Yeah, I agree with you, Professor Chuan Zhang, that to increase the use, and also to attract more users, I think we need to make it more easy to use. All right, so and I also would like to hear from Lirong regarding the how to improve the use and interpretation of the model results, because your project is funded by UK, and also you also have a few projects funded by European Council. I'm just wondering, what is your take on open sourcing? Because usually these kind of projects mandate that you have to make the codes open accessible, and also and do you think open sourcing will help improve the use and interpretation of integrated system model?
Yes, absolutely. I strongly support open research, but just to add maybe two quick notes based on other panelists' comments already. The first thing is I think open research should go beyond the traditional open access publications. We should include any tangible products arising from the research, like open data and maybe open modeling. This is the first way to move forward. And the second thing I think is maybe the people here, we are all aware of the IAM models, but for the wider research communities, I think the first thing we need to do is to improve people's awareness of this model. And after that, I think maybe some interdisciplinary discussions, to help people to know what questions the IAM model can answer and how this model can be used in their research domains. I think that's another thing we need to work together.
Okay, thank you so much for sharing your thoughts, and also I'm looking forward to more results from your project, also from results from other speakers. I think we are already at time, and I think it's already 7:05, 7:05, in Chinese time. I think now it's already 11 something. I think 5:11 in UK time. And thank you all so much for staying with us. Also thank you the audience so much for staying with us. And I think we are coming to the end of the session. And I would like to say thank you to all of the speakers for your great presentation, also for this great discussion. The integrated assessment model community, also the industrial ecology community, have been, very active, in the discourse about carbon neutrality and other sustainable development goals. And I believe, our community, the two communities can contribute more, to the discourse about carbon neutrality and sustainable development, and also hoping that in the future we can have more opportunities to interact, to share our research outcomes, also to have more in-depth discussion about how we should move forward, how we should do differently to make our community more successful. Right, and I think we are at a time, and also if you have any question, if the audience have any question regarding the 5 speakers, the presentations, please send them email. I've already left all the information about the speaker on our ISIE website, and also if you have any direct questions to the speakers, please you can also reach out to me. I can forward your question to the speakers. Again, thank you so much for staying with us, and I hope you have a good day and also a good night. And thank you so much.
Oh, thank you
Bye.
for organizing.
Thank you. Bye.
Thank you. See you.
See you.
Bye.